Hello and welcome. My name's Andrew Edelston. I work at NVIDIA on the DLSS team. And today I'm going to be walking you through a little bit about how the DLSS technology works and also how you can integrate DLSS into your game. So what is DLSS? Well, it stands for Deep Learning Supersampling. And it's a real-time reconstruction technique that we've come up with that uses deep learning to allow a game engine to render to a small size and then output to a larger size. We use the tensor cores that are available on the RTX line of hardware, and it was launched with the Turing architecture in 2018. So since that time in 2018, we've been busy. We've launched over 55 games with DLSS, working with our wonderful game partners across the industry. And as you can see from this list here, we've got games in all sorts of genres. We've got first-person shooters and strategy games and battle royale, and DLSS really works across the board. So we have been busy, but we're keeping on being busy. We're always looking for the next DLSS game, and at Computex, we recently announced the next tranche of DLSS games that's coming out. Once again, you can see there's a nice array of games: action games, survival games, builder games. We've not only been working with game partners, we're also working with our game engine partners. You can see in the center of the slide here, we've worked with a lot of first-party game engines. Now, these are engines that are run and used by large game publishers or large game studios. And we've also been working with Unity, who've announced DLSS is coming to their 2021.2 engine, and also with Epic for Unreal. We now have a DLSS plugin for both UE4 and UE5. And I'm very excited today to be able to announce that we're actually making the DLSS SDK available to everyone. So if you have your own engine or your own game and you want to put DLSS into it, you can go to the developer site, grab the SDK, and get started. DLSS supports DX11, DX12, Vulkan, as well as Windows and Linux. And we recently announced support for Proton. So for those who like Windows games but on Linux, we've got you back there as well. The SDK includes everything you might expect: headers, libraries, helper files, a sample that you can look your way through, and also documentation to help you get going. So how does DLSS do these remarkable things that we've seen it do? Well, the key is in the name. At the core of DLSS, we have a deep learning neural network. As DLSS is based on a neural network, how do we train that neural network? Well, like you may have heard with AI, it takes a lot of data. We have low-resolution frames. These are rendered at 1080p. They're based on different inputs, mainly color and motion vectors. We'll go through the inputs a bit later on. And then we feed that into our supercomputer, and we ask the model to create a 4K color output. Now that frame is then checked against a super high-resolution ground truth. Now, this ground truth is actually rendered at close to 16K, so it's much too high resolution to be run in real time, even on the latest, greatest hardware. But it gives us something to aim for. And so we take that ground truth and we check it against the 4K image. We compute the differences, and then we feed that back through the supercomputer as part of a process called backpropagation. During that process, the supercomputer adjusts millions of parameters that are within the neural network. Then we go to the next frame, and we do the whole thing again. And this goes on, again and again, millions and possibly by now billions of times. And all the time, the neural net is being finely adjusted to make it perfect at taking low resolution and creating high resolution. So let's look a little bit closer at how that reconstruction works. If we focus on the top left here, we can imagine we have a piece of geometry moving across a 1080p screen. And on the right-hand side, we have what we want, which is that same piece of geometry, but at 4K. So you'll notice in each pixel on the 1080p, we have one point, one sample. Unfortunately, when we go to 4K, each one of those low-resolution pixels represents 4 pixels. And so we have to try and figure out how to fill in those extra pixels. If we just take a very naive approach like we have here, we would simply check the low resolution pixel. Was it black or was it white? If it was white, we fill all 4 pixels in white. If we're a little bit smarter about it, we add a second frame. So now we have 2 samples to pick from, and now we can be a little bit smarter. Maybe we don't color in all the high resolution pixels white. We do some black and some white. And if we add a third frame, now we have even more information, and maybe we do 2 white and 1 gray and 1 black. And then because we're using deep learning, we always want more information. We're going to help the neural network make a better decision. And that's where temporal feedback comes in. So temporal feedback comes in 2 forms for DLSS. Firstly, there's a feedback loop within the model itself. It's feeding information back to itself. And then secondly, we use motion vectors that are calculated by the engine. And they track how a pixel came to that position on the screen and where it was in the previous frame. Once we add that to the mix, we feed all that previous frames, all the temporal information, and we feed that into the model, and it's able to make a very informed decision about what those high-resolution pixels should look like. Then we end up with something that's very close to a native resolution render. If we look at this in a different way, we might compare what we get when we use native resolution rendering, traditional upscaling, and DLSS. So in this first row, we have native resolution. This is where we're rendering, and every pixel that we render has a perfect match to what we display. If something's black, it's black. If something's white, it's white. There's no work to do here. Traditionally, we use upscaling, and it's spatial. So that means we only have 1 frame. We don't know what we did last time. And therefore, we have to make a series of guesses or estimations, and this can lead to problems. So if I'm looking at how to fill in these pixels, these high-resolution pixels, I might look at my neighbors. So when that first sample hits, maybe it's black, but the pixels next to it might be white. So maybe I make the high-resolution pixel gray. The problem here is we start averaging, we start blurring, we start making things gray when they should be black and white. And this is what we typically associate with upscaling. We get a blurry image. The other problem is we only are dealing with 1 single frame, and we don't know what we did in the past. So maybe this time we decide something should be white when the last frame it was black. And that leads to flickering, and the human eye hates flickering. In the final row, we see what DLSS is doing. That's what we talked about in the previous slide. We're using multiple samples. We're using temporal information, and then we're making an informed, smart decision on how that final high-resolution pixels should look. So pictures speak 1,000 words, and here we have the wonderful game Control from our friends at Remedy. On the left-hand side, we have native rendering. So this is the Control game engine rendering at 4K. In the center, we have DLSS. The game engine's rendering to 1080p, and then DLSS is bringing that up to 4K. And on the right-hand side, we're using the NVIDIA control panels upscaling, which is a spatial-based upscaler like we were just discussing. If we look at the video here, you'll notice as the camera pans up, in the right-hand side, the tree is scintillating, is flickering. That's some of those guesses that we were talking about not being correct frame to frame. If you compare the DLSS and the native frame, they're almost identical. And that's the power of DLSS. So that's how DLSS creates the image. But DLSS's main job is actually to bring back performance, give you higher frame rates. So let's have a look at that. So DLSS offers different levels or different quality modes. And these are quality, balanced, performance, and ultra performance. These allow for 2x, 3x, 4x, and even 9x scaling. So ultra performance, which is targeted at 8K gaming, allows the rendering engine to render to 1440p, and then it scales it all the way up to 8K. Typically, we're seeing people use quality or maybe performance mode. And there's an example here in the wonderful game Fortnite. You can see the massive performance boost we get. If we render using native 4K, we're sort of under 30 hertz. If we use performance mode with DLSS, Suddenly we're up to 73. So here we're going to take a closer look at that screenshot from Fortnite. Again, you can see that there's a nice high frame rate on the right-hand side. And we'll zoom in on this section here on the right. Notice the way that the shadows, the edges of the dock, they're still very sharp. They match the native 4K resolution. But again, that frame rate is way higher, and that's the power of DLSS. Another example of a performance boost, the game Cyberpunk 2077, which everyone knows is graphically amazing, but it's also graphically very taxing, even on our most top-end GPUs. So if you attach a 4K monitor, you turn up all the graphic settings and you turn on all the ray tracing settings, even a 3090 and a 3080, they're going to struggle with frame rate. That's where DLSS comes in again. So with DLSS in performance mode, now the rendering engine doesn't need to render to that full 2160p resolution. It'll actually render to 1080p and let DLSS do the work to bring it up to the 4K monitor. So I hope by now I've convinced you that DLSS is good. It's something you want. So how do I go about now putting it into my game? So what do you need in your game to put DLSS into the engine? Well, there are a couple of things. Firstly, you need to be able to upscale. That should go without saying. You also need support for subpixel jitter. You need per pixel motion vectors. We'll talk about both those things in just a moment. The post-processing chain should also be upscale aware. We need the depth information most 3D engines have nowadays. And we also need to be able to bias things like the texture, mipmap selection, LODs, and even things like decals. And we'll talk about that a bit later on. So where does DLSS live in the rendering pipeline? Well, DLSS works in screen space, so it's happening after rasterization, rendering, ray tracing, that type of thing. It should be happening right at the start of post-processing. And indeed, if you can make it the very first thing in post-processing, that's the absolute optimal position. There are certain post effects like blurs, depth of field, that move pixels around. That can affect how the feature tracking inside the neural network works and can lead to artifacts from time to time. So it's best to put DLSS right at the front. The call to DLSS itself is pretty straightforward. DLSS is just a library, and we send down the color frame with jitter and without anti-aliasing. We'll talk about why that is in the next slide. We also need motion vectors, depth, exposure, and a few parameters. The previous frame is actually that temporal feedback, and that's handled inside the DLSS library. The output from DLSS is the high resolution color frame, and that gets passed back to the post-processing chain and then processed down the rest of the chain and out to the display. I've mentioned jitter a couple of times. So what actually is jitter? So jittering is when we very subtly adjust the viewport. So even when the camera isn't moving in the 3D world, we still want information to be flowing to DLSS. If we look at the frame on the right-hand side here, if the camera's not moving and we just keep sending that exact same frame to DLSS, it's not going to be able to reconstruct the edges or the curves very well. What we want is for the frames to look like this. Now this may look horrible to a human. It's sort of jittery, but this is exactly what we need for DLSS. So let's zoom in here and have a look at this little funky flamingo. You'll notice that the curve on its neck, the curve on the railing, is very pixelated. It doesn't look very nice to a human eye. But that, again, is exactly what we need. So if we start jittering, we start moving that frame, you can see now that the edge is moving ever so slightly. And that's exactly what DLSS needs. It needs that extra information. It needs those extra samples to properly reconstruct the high-resolution image. So as we just saw, we need to jitter. We need to give DLSS that extra information, but we don't want to shake. We don't want the frame moving around and being perceptible to the end user in the final frame. So to do that, we need to adjust the viewport just slightly. We need to be within 1 pixel, actually, of the origin. So therefore, when we do our offset to the camera projection matrix, we need to just be within negative 0.5 and positive 0.5 for the X and the Y coordinates. The other main input is motion vectors. Now, these are calculated by most game engines. If you're using TAA or you have things like Motion Blur, you're probably calculating these already. But these describe how a pixel is moving across the screen. So as geometry moves, the engine keeps track of that, projects it onto the screen, and then it gives us a vector that points back to the previous location from the previous frame. So here in this very simple example, the bright green dot has moved 5 pixels down and 4 pixels across from the light green location. Now here we've used full pixel values, but you can use partial, it depends on your engine. Some engines use a different scale for their motion vectors or a different space. That's perfectly fine as well. You just need to send that through as the motion vector scale to DLSS. The one thing to look out for is make sure you don't send 0, because that'll cause havoc with the feature tracker. So that's the basics of how to integrate. Unfortunately, not all integrations work first time. So to debug an integration, there are some very simple things you can do. First thing is get an image on the screen. That might sound a little silly, but that's a big first step, and that's you're well on your way to getting DLSS working once you've got that. Then after that, it's the simple things. Just take some screenshots. Take a screenshot with DLSS on versus off, turn some post-processing on and off, look for differences, look for problems that might come up, and do A/B comparisons. DLSS also has some built-in debugging tools, and the great thing about these is that they're real-time. So you can actually have these on screen while you're running your game and be getting information and doing live debugging. The first one we'll look at is this box of text you can see down in the bottom left of the screen here. So this will give you information about the DLSS version, whether you're running Vulkan or DirectX, also the resolution, the input and the output resolution, along with hotkeys for some of the tools that we have that are inbuilt into the development DLL. The other great tool appears in the top right that you can see up here. Now, this is what we call the debug overlay. This will show certain things. It'll show the raw input without any processing applied. It'll show you a visualization of the motion vectors, a visualization of the depth, and also what we can see on screen here, the jitter offset viewer. So this is showing you the last 20 or 30 offsets that were received and whether or not they're inside that 1 pixel border around the origin. So as we saw earlier, we've been busy. We've done a lot of game integrations now. We've probably done 60 or 70 different games, and most of those are in different engines. So we've seen a lot of common occurrences. So what are the types of things we want to look out for? Well, firstly, don't just assume, hey, DLSS is in, it's working, it looks okay. I guess, it's doing upscaling, so that's probably good enough. Not so with DLSS. DLSS should very closely match your native resolution. If you're seeing things like shaking, blurriness, edges that are too jagged, or objects that are missing anti-aliasing, or indeed anything that looks out of place, there could be something wrong with the integration. So now we're just going to work through some of the more common integration issues that we've seen and had experience with. So firstly, we sometimes hear, hey, I turned on DLSS, everything looks terrible. It's jittering around all over the place, there's jagged edges. Well, is DLSS actually running? The easiest way to pick that up is just to turn on that debug text. If you can see it, at least DLSS is running and we can move on from there. The other problem we see often is with jitter. Now, different engines apply different jitter patterns. They calculate their projection matrix in different ways, so that can sometimes lead to problems. It's a little bit detailed. We're going to do a follow-up developer blog, so keep an eye out on that. Today, we're going to step through what happens when some of those biases are missing, what happens when post effects aren't aware of an upscale taking place, and then we're going to have a look at how to look for motion vector problems. So the first thing to know for rendering biases and I'm going to be repeating this, render resolution is no longer equal to display resolution. So that affects a lot of different things. Things like which MIP to pull out of a MIP chain, which LOD to use, whether an object is visible anymore, usually highly affected by the density of the render target. And that has to be adjusted now because the render target and the display target are different. So you need to factor that in. Less common problems, sometimes we see particle effects and decals having issues. We'll have a look at one of those in a second. For right now, we're going to zoom in on Rust from our friends at FacePunch, and we're going to look right at the center of the screen here. So if we look at the top of the screen, we see that's what native rendering looks like with TAA, and then in the red rectangle at the bottom, that's DLSS. So something's wrong with DLSS. Everything's blurry. We can see that straight off the bat. The terrain, the rock, the grass is way too coarse. So what's happening here is when the MIP is pulled out of the MIP chain, it's going too far down. It's going too coarse. And that's because it's not factoring in the difference between the render resolution and the display resolution. What we need to do is put in a bias using the algorithm you can see on the screen. We need to factor in that there's a different ratio now. Now, one thing to point out, you do need to use your MIP chain. You can't just say, well, I'll just use the highest MIP and be done with it. That will not work. You'll end up with horrible sampling issues just like you would in native rendering. So you still need to use the MIP chain. You need to put in the bias though. The other thing we see from time to time is we get reports that, hey, I turned on DLSS and this disappeared or that disappeared or this texture changed. Well, DLSS itself cannot remove an object from a scene. However, it can be affected again, perhaps from the LOD system. Maybe it's calculating visibility using the render resolution. So we'll have a look at an example here in the wonderful game Doom Eternal. And we're going to play a little bit of a guessing game or a spot the difference game that we used to play when we were kids. So if you have a look at that highlighted area, on the top we have native resolution using ID's TSAA algorithm, and on the bottom we have DLSS. Now something's different. If you said the logo, you win the prize. When ID first put DLSS into Doom, this problem was happening. Some textures on different buildings were disappearing. Now you think to yourself, well, the textures in the model, like if the model's there, surely why would the texture be changing? Well, for these particular logos, ID was using their decal system. And they had to slightly modify the decal system because the DLSS scaling was happening now. Once they did that, everything was fine again. The next thing we'll look at here is actually two problems, and they both have, again, to do with this difference between render resolution and display resolution. The post effect, in this case, depth of field, is not factoring that in. So if we look at the red rectangle, you'll notice the background is really blurry. You can barely see the railing anymore. And then similarly, if we look at the reflection in the mirror, again, it's too blurry because it's not factoring in the render and display differences when it's calculating its distance calculations. So both of those things had to be fixed. Another example of a post process that isn't quite working is from Watch Dogs Legion by Ubisoft. So here, if we look at the top, which is native resolution with TAA, and then we look at the bottom, which is DLSS, we notice that the DLSS frame, it seems a bit warm. It seems that the reds and the pinks are coming through too strongly. If we zoom in, we get a hint as to why. So we'll take a look at this little bridge up here. Now this is taken at sunset. So the sun is having a large effect on the environment, but the chromatic aberration effect is actually amplifying that. It's pulling those colors and separating and then making the reds and the pinks bleed into the surrounding pixels. And again, this is something that would need to be fixed. And again, factor in that difference between render and display resolution. The final thing we're going to look at is how to debug potential problems with motion vectors. So when things are moving, if there are artifacts, one of the first things we look at is whether the motion vectors for the object are correct. And we can use the debug overlay for that. So here we're standing still in Doom Eternal. So we can see that there are motion vectors on the gun and the hands because the player is breathing. So that's correct. We can also see off to the right-hand side that there are motion vectors, and that's actually on the ocean, which is outside the building. Now, there are some sparks in the top left of the screen. They are particle effects, and they probably won't have motion vectors, but if there was any geometry associated with them, maybe that pipe that they're sparking out of, maybe that was moving, that should probably have a motion vector. So if there was a problem with that, that would be something to take a look at. So that's a little run through of the DLSS technology, how it works, how to integrate it, and indeed how to debug it in your engine or your game. But what do you do now? So for you guys, go out there, grab DLSS. If you're in Unity or Unreal, go and look at your engine sites. If you have your own engine or your own game, please jump onto the developer site, grab DLSS, look through the SDK, work through the sample, and see how you can get it integrated into your game. If you put it in, your users will love you. They're going to get nice higher frame rates, all from the power of deep learning. And as for us, well, we keep on keeping on. We're continuing our research. We're looking for ways to make DLSS faster. In particular, a couple of things we're looking at is when objects are disoccluding, when they're coming out from behind other objects. How do we hold on to them as quickly as possible? How do we improve the feature tracker? And then similarly, when an object doesn't have a motion vector, like if it's a particle effect or maybe RT shadows or something like that, how do we train the neural network to hold on to that feature even though motion vectors might be missing? And finally, we're very excited to announce that our Ray Tracing Gems 2 book is ready for release, and it'll be coming out on the 4th of August this year. You can order it for digital download or in print version. And as a special celebration of the release, we've done a hard copy limited edition. And if you would like to win a copy, head over to the address on screen, put your name down. All the best of luck with that. It's a wonderful book, and I hope you enjoy reading it. So that was the DLSS technology. I hope you understand now a little bit more about how it works and how you can put it into your game and all the wonderful advantages that DLSS can bring. I wish you all the best. Take care.